Alright, now let's try to discuss a couple of examples involving these results. I would like to start the first example with something fairly simple. Alright, so suppose I give you this example that let's say an amount of $10,000 invested at an interest rate of 10% that compounded continuously. We would like to know how much will be in the bank account after 10 years, how much will be accumulated in the account after 10 years. Let's try to answer this question. First, let's write down what is given. Alright, looks like the initial deposit is given. Again, pay attention to the wording. I am calling it initial deposit. This is how I write down initial deposit. I'm going to denote it by A0. Alright, so initial deposit is 10,000. When we say initial deposit, the time when the deposit is made must be considered as t equal to 0. My intention is very clear. I am going to use these two values as initial value to get the particular solution of my differential equation. Okay, all right, so we have initial deposit and time t equal to 0. Interest rate is given. This is 10%. Remember, to convert percentage value into numerical value, you have to divide that entry by 100, right? So if you divide 10 by 100, you get 0.1. Okay, so interest rate is 0.1. So rate of interest is 0.1 then. Okay, and then the time limitation is given. We would like to know how much will be accumulated in the account after 10 years. Okay, as I said, the differential equation, you first have to decide which case are you dealing with, and based on that write down the differential equation, and then plug the values for constant and try to solve it. Okay, so first and foremost, I want you to think about it for a second that this is really a simple case where amount is deposited into the account with a certain interest rate for certain period of time. There is no mention of continuous deposits or continuous withdrawal being made. Alright, so this amount grows according to that first simple formula that I call continuous compounding formula. Alright, so let's write it down. The amount grows according to this formula, dA by dt equal to R times A, with initial data A at 0 equal to A0. Throw the values. Alright, when I say initial deposit, time is automatically considered as t equal to 0. This is at the time when deposit is made. Okay, we have the value of R, we have the value of initial deposit. The differential equation will take the following form: dA by dt equal to 0.1 times A with initial data whenever t is 0, initial deposit is $10,000. Okay, as I said, this differential equation is separable as well as first order linear. It is separable because variable A and variable t can be seen separately in terms of factors on the right hand side. It is first order linear because dA by dt term, it's followed by, you can always send this term over to the right hand side. You have dA by dt term and then a to the power 1 term, and then right side function is a 0 function, constant function. Alright, now I mentioned in the previous video that it is recommended that you use first order linear differential equation method for this type of example. In this example, you are going to get answer to that question, why did I say that? Okay, So first let's try to solve this example using both method. Okay, separable DE method, I'm very sure that most of you guys are going to like that because that's simple method, no? So let's try to solve it using separable DE method first. Okay, so I'm going to solve this differential equation using separation of variables. I have dA by dt equal to 0.1 times A. Let's separate the variable. Let's send A on the side of dA. And then we are going to move dt over to the other side. Okay. So this is a differential relationship. On one side I have a pure function of A along with dA. On the other side I have a pure function of t along with dt. All I have to do is integrate both sides with respective variables. And I am done. Think about it. What integration technique are you going to use? Direct matching, direct matching. Alright, let's do that. Antiderivative of 1 over A is going to be log absolute A. Antiderivative of 0.1 with respect to t is 0.1 t plus some constant of integration. Let me put k. Alright. Okay. Now remember, being money, A is a positive quantity. Alright. So it's okay to get rid of absolute value sign. You can just write log A equal to 0.1 t plus k. Now remember, A is the amount in the account that changes over the time. It's a function of time. We really want our solution to be in terms of A as a function of time. That means we need to get rid of that natural log from the front. Alright. Now remember, to get rid of natural log from the front, you need to use the fact that exponential and logarithmic functions, they are inverses of each other. To get rid of that ln, I will have to apply e on both sides. Look, this is what I get. That's obviously identity. You are gonna get that input back. Get A equal to, I get e to the 0.1 t plus k. Alright. Now look, constant of integration, it went into the power of e. Now this is slightly bizarre form. So what I'm gonna do is I will try to use the properties of exponent. Remember, this is the property of exponent I would like to use. X to the a plus b is x to the a times x to the b. As I said, you have used this property in this direction many times. We would like to use that property in the opposite way. So I would like to split that constant. I would like to write that constant separate from the variable t part. Okay. Alright. Being a constant, you don't have to write your constant in such a weird form, e to the k. If k is constant, e to the power k is going to be constant. No need to write constant in such a weird form. So let me use c in place of e to the k. Alright, so suppose or assume that e to the k is some constant c. Now let me mention here that transition from here to here is not trivial for many students. In fact, for many students this is a very tricky transition. They don't understand why we change that e to the k to c. E to the k is a constant there is no need to write constant in such a weird form, so I adopt a brand new symbol for that constant of integration, and I call it C. All right. That was the only reason why we did it that way. Okay, so looks like that is the general solution of my differential equation. Need to find out the particular solution. Okay, let's do that. I have the initial data given. Look, put t equal to 0 and a equal to 10,000. Let's do that. If I plug it in here, I get 10,000 equal to c times e to the 0.1 times 0. Looks like we get e to the 0. E to the 0 is 1, so that tells me that my c has to be 10,000. Okay, I can write down the particular solution. Particular solution is going to be a equal to 10,000 e to the 0.1 t. Now think about it. What does particular solution represent? Particular solution represent amount in the account at any time t. It's a function of time. Okay, if I ask you what is the amount in the account after 10 years, all you have to do is plug t equal to 10. If I ask you what's the amount in the account after 20 years, put t equal to 20. If I ask you how long does he need to wait to get $50,000, plug a equal to 50,000 and solve for t. So these are the various type of examples that one can construct. Alright. Now for our example, we would like to know what do we get after 10 years, right? So after 10 years, want you to plug t equal to 10 there, get 10,000 e to the power 0.1 times 10. 0.1 times 10 is just 1. Remember what is e? Approximately 2.71, no? If you multiply it by 10,000, you get 27,100, right? This is the amount that the person is going to get at the end of the 10th year. All right. Okay, so that is the solution of this problem using separable differential equation. We can solve it using the first order linear differential equation as well. Let's try to do that. Okay, so for that I am going to write down this problem in the standard form first. Coefficient of dA by dt term is already 1. That term needs to follow by a to the power 1 term, so I'm gonna move that 0.01a to the right, to the left side, and then the right side will have 0. And then I have initial data. It suggests that when t is 0, E0 is 10,000. Alright. Step 2. Collect the data. Write down the coefficient function. Coefficient function is constant here. Right side function is 0. Initial, these are function of time, right? So coefficient function, right side function, write down g of t. Initial t value is 0. Initial deposit is 10k. Okay. All right. We are ready to find out integrating factor. Remember, integrating factor is also function of time, variable t. I get e to the power 1 antiderivative of negative 0.1 dt. Antiderivative of that constant is e to the negative 0.1 t. Alright. We are ready to write down the general solution. Remember the formula for general solution? A equal to, we had y equal to in that formula. Here our dependent variable is a, independent variable is t. So write down the formula in terms of a and t. It's the antiderivative of g of t times integrating factor, so 0 times e to the negative zero point 0.1 t dt plus c divided by the integrating factor, right? 0 multiplied by anything is 0, entire derivative of 0 is 0, so I really get a equal to c over e to the negative 0.1 t, or I can write it as c e to the negative 0.1 t. See, this is our general solution. Now think about it, what is the benefit of using first order linear differential equation method? I don't have to solve that weird form for x, alright? And this is the reason why I said use the first order linear differential equation. Your textbook is using separable dE method. I want you guys to use the first order linear differential equation method, because that gives you the solution explicitly in terms of a as a function of time. Okay, the remaining steps are the same. To find the particular solution, I'm going to use the initial data, put t equal to 0, a equal to 10k. I get 10,000 equal to c times e to the 0, or c equal to 10k. So particular solution is going to be a equal to 10k e to the e to the 0.1 t. This is plus 0.1 t. Okay, the solution, particular solution, is going to be the same no matter what method you use. After 10 years, it's clear that all I have to do is plug t equal to 10. I get 10,000 times e to the negative 0.1 times, sorry, positive 0.1 times 10, and that's 10,000 times e, or 10,000 times 2.71. I again get the same result, 27,100. Okay, all right. So this is the first and the simplest example that involves continuous compounding. Let's try to make it slightly more interesting by creating something that uses either continuous deposit or continuous withdrawal. Okay, so here is the next example. Let's say John deposits, let's say $20,000 in IRA that pays let's say 5% interest, right, compounded continuously for his retirement. In 20 years. Suppose John wants to retire in 20 years and he initially deposit $20,000 in IRA account that pays him a very nice interest rate of 5% per year. Okay, he intends to make continuous deposits of let's say $1,000 every year. Until his retirement, obviously. The question is, how much will be accumulated his account at the time of the retirement. Alright, as I said, it is highly recommended that you guys use the first order linear differential equation method because chances of errors are significantly small. If you use separation of variable method here, then you will have to deal with use substitution method, right? And then of course you will have to convert. You will have to write down your answer in form of a as a function of time, which requires getting rid of log from the front, which is not really a simple task. All right, so it's a tedious work. Not saying it's difficult, can be done, but it's long work, okay, compared to what we are gonna do to solve this. Okay, so here is the solution. Write down what's given first. Initial deposit is given, that's 20k. When you write initial deposit, at the same time write down t equal to 0 so that you know that it's the initial condition. Okay. Interest rate is 5%. I'm gonna convert that into numerical value by dividing it by 100. Timeline is 20 years. Okay, and then there is an additional information regarding continuous deposit. So this continuous deposit are $1,000 every year. Okay, I'm gonna write down the differential equation associated with this situation. The DE are gonna be dA by dt equal to RA plus D with A at 0 equal to A0. All I have to do is throw the numbers in. Okay, I'm gonna throw them in here. I get dA by dt equal to 0.05 A plus 1000 A at 0 equal to 20k. Okay, all right, let's solve it quickly. Okay, first step, write it in the standard form. Coefficient of dA by dt term is already 1. Next term needs to be a to the power 1 term. We just move that a to the power 1 term over to the other side, equal to 1k. A at 0 equal to 20k. Okay, step 2, collect the data. The coefficient function p of t negative 0.05, right side function g of t 1000, initial time 0, initial deposit 20k. Okay, all right, so we have all the data collected here. Step 3, I need integrating factor, one entire derivative of negative 0.05 with respect to t. Okay, I get e to the negative 0.05 t. Need to calculate the general solution. A equal to product of integrating factor times right side function. Again, make a habit of writing this product in the canonical form so that computation will be simpler and faster, plus c divided by the integrating factor. Okay, very carefully think about it. What integration technique are you going to use to integrate this? Obviously direct matching with the formula. Let's do that carefully. 1k e to the negative 0.05 t over negative 0.05 plus c divided by e to the negative 0.05 t. Okay, This is 5 divided by 100, bottom of the bottom goes into the top, or 5 divided by 100 is 1 over 20. Simplify this carefully, I get A equal to negative 20k e to the negative 0.05t plus C divided by e to the negative 0.05t. Now, if you notice that e to the negative 0.05t is part of one term in the numerator and it is in the denominator as well. Alright, you can split the denominator over both terms and write your general solution in this form: negative 20k plus C times e to the 0.05t. Now think about it, what did I do here? Alright, I distributed that denominator, I split that denominator over the first term, so cross out e to the negative 0.05t from top and the bottom of the first term. Second term has got e to the negative 0.05t in the denominator. If you shift that denominator up in the top, then exponent will be positive. Alright, so that's what you are going to get. We get a very decent form of the general solution. A equal to negative 20k plus C e to the 0.05t. Okay, need to find out the particular solution. Let's do that now. Use the initial data. When t is 0, plug A equal to 20k. Okay, let's do that. A equal to 20k. On the other side I have negative 20k plus C e to the 0.05 times 0. E to the 0 is just 1. I'm gonna move that 20k over to the other side. 20k plus 20k is 40k, and then e to the 0 is 1. Out of infinitely many choices of C, this is the one that satisfies our initial data. Alright, so particular solution is going to be A equal to negative 20k plus 40k e to the 0.05t. It's a pure function of time. Now we can answer the question, how much is he going to get in 20 years? Let's do that. So after 20 years, at the time of his retirement, he's gonna get negative 20k plus 40k times e to the, this is 5 over 100 times 20, and that's 100 over 100, so it's 60 to the 1. I get negative 20k plus 40k times E. E is approximately 2.71. Let's consider 2.7 for this example. I just want to get answer quicker. I get negative 20k plus 27 times 4 looks like it's 108. 108 and then 0, 0 is 0. Okay, looks like 108k minus 20k. Let's subtract. If you subtract this, you get let's say 88k. Alright, so that is the amount that he is going to get at the time of his retirement if he initially invests 20k and then every year he add 1k to it. So remember, 20k is being invested, 1k every year for next 20 years, so 20 plus 20, 40k. It is quite obvious that the final amount needs to be bigger than 40k. If you get your answer less than 40k, then you are doing something wrong. Okay, so be sure that this amount needs to be bigger than initial deposit plus number of year times the constant deposit that is being made. Okay, all right. Now what I want you guys to do is try to construct one more problem very similar to this by yourself and try to solve it. For example, you can construct something like this. Let's say Jack won lottery of $100,000. He put that in some saving account that pays interest rate of 10% compounded continuously, and he intends to make continuous withdrawal of $10,000 every year. How much will he have left in his account after 5 years? All right, try to answer this question. If you have any question about any of this material, feel free to shoot me an email. I'll be more than happy to clear your doubts. Thank you very much.